In this lecture, we're going to finish up the indefinite integral, and then we'll use the fundamental theorem of calculus to apply what we've just learned to definite integrals, and then we'll also talk a little bit about the area between two curves. So for the rules of integration, we have two parts left. We need to figure out the natural rules and the trigonometric rules for integration. So the idea is, do we know how to take the integral of e to the x dx? And hopefully when you look at that, you say, okay, do I know a function whose derivative is e to the x? Because that's what the indefinite integral is telling you to do. Instead of thinking about an area now, we think of an antiderivative. So you think, oh yeah, e to the x, because the derivative of e to the x is e to the x. And of course, you can plus any constant. So it could be plus 0, it could be plus 1, plus 2, plus a half, plus any constant, because the derivative constant is 0. And then, of course, for trigonometric functions, we want to ask the question, can we integrate, let's say, cosine of x dx? And again, we can memorize some rules, but this one's not too bad either, because you ask yourself the question, do I know some function whose derivative is cosine of x? And that's supposed to be cosine, not co-x, so there's an s there. And you say, oh yeah, I know sine of x, because the derivative of sine of x is cosine of x, and then plus c. And we'll talk, more about how this works. And so let's just get started. And so here's our first example. We want to integrate these two functions. And the rules, the natural rules, and you can look at your sheet here. There's two of them. And the first one we just did, the integral of e to the x dx. And that's equal to e to the x plus c. And then we have the rule, the integral of 1 over x dx. And here you have to be a little bit careful. I want to say, okay, do you know a function whose derivative is 1 over x? And of course, hopefully you say ln of x, then plus c. And that, for me, is fine, but you'll see in your other courses, you need to make sure you put absolute value of x. And the reason we do this is because if you think about this 1 over x can be negative here. And so in order for this to make sense, you need to put an absolute value on here. And you can relate these two things. I don't want to go on a tangent because it would take me a few minutes, but you can see, if you really want to, you can graph ln of absolute value of x. And it would look like this. It looks like the same on both sides, just heading down to negative infinity here, and then going up to positive infinity very slowly here. So if this is your function, you can actually check, and if you think about what this derivative is, on the right-hand side, this is just ln of x, so it looks just like this. And then on the opposite side, it's going to look like this. And you can think about it, it's sort of the rate of change here, it's going towards 0. Whereas here it's getting more and more negative, and that's what this is basically said. The rate of change is. This is basically what this says, and this is 1 over x. And so here you're taking the derivative. So you're kind of trying to figure out, why do I put those absolute values on there, so how these correspond. All right, so let's get to some examples. So let's do part A, the integral of 3x minus e to the x dx. And this is not that hard. The first one's a power rule, and the second one is this first rule for the natural function. So the integral of e to the x is e to the x. And so you simply add 1 to it, divide by it, minus the integral of e to the x is e to the x, and then you gather the c's on the end, so just plus c. And that's my answer. So these are nice and easy, really. Part B has a bit of a twist to it, because when you look at it, it doesn't look like any of your 4 types. So basically how you integrate is you have to recognize the thing that you're integrating as being one of your types. And when I say types, right now we have just 4 types. We have the integral of a constant dx is equal to the constant times x plus c. We have the integral of a power of x to the n dx, equal to, you add 1 to it and divide by it, plus c. And then we just saw the integral of e to the x dx, of course, is equal to e to the x plus c. And finally, the last type that we know is the integral of 1 over x dx, which is equal to ln of absolute value of x plus c. So these are my 4 types right now. And if something doesn't look like one of these 4 types, I can't integrate it. So as an example of something you can't integrate, you cannot integrate the integral of 1 over 1 plus x squared dx. There's no way, no matter how hard you try, that you can turn it into one of these 4 types. And so if it's not one of my 4 types, I'm out of luck. I have to come up with something else, some other way to do it. And so in part B, the idea is it at first doesn't look like one of my 4 types, but I can do a little algebra and turn it into one of my 4 types. And so the trick is, when you divide a sum or a difference by x, right, you can give it to both terms, so that you can pull it apart basically. So you have x cubed over x minus 1 over x dx. And you know, the way I remember this is I know how to add fractions. If I take 1/3 and I add 4/3 to it, that's the same as 1 plus 4 over 3. So instead of putting them together, finding a common denominator and adding the numerators, I can pull them apart too, and that's what I'm doing here. I'm just pulling them apart. And so this is equal to the integral of what, x squared minus 1 over x dx. Now notice I did not write this as x to the negative 1. Right, the reason is because this is one of my 4 types. So if you look over here, this integral of 1 over x dx corresponds to this type, and so I should be able to integrate it by using that rule. And so this is equal to, the first one's the power rule. You add 1 to it, divide by it, minus ln of absolute value of x plus c. And it's all done. Now, as a side note, let me tell you what students often do here. A lot of times when they make this sort of transition from here to here, what you're going to do is you're going to say, okay, this is equal to the integral of x squared minus x to the negative 1 dx. You'll add 1 to the power, just like you did before, so you get x cubed over 3, minus, you'll add 1 to the power, so you get 0, and then you'll try to divide by it, 0 plus c, and that's where you make your mistake, because you can't divide by 0. So you know you did something wrong. And if you look back at the rule on your sheet, you'll notice that this is true as long as n is not equal to negative 1. When n is equal to negative 1, you're down here in this case, and it has its own special rule. So just be aware of that. Otherwise, they don't cause too much trouble, really. Okay, let's talk about the trigonometric rules, because there's a bunch of these. And the way that I typically remember them is I know the rules for sine and cosine. So I know the rule for the integral of, let's do cosine of x dx, that's the first one on your sheet. This one is equal to, and I try to think of a function whose derivative is, excuse me, whose derivative is cosine of x, and that's sine of x plus c. And then below it you have the integral of minus sine x dx, and that's equal to, of course, cosine of x plus c. Now what happens if you didn't have that negative sign there? So let's just think for a minute. What if I had, instead of the integral of negative sine x, I just had the integral of sine x dx? Hopefully you would say, okay, well, I know it's probably cosine of x plus c, but if you take the cosine of x, you get negative sine of x. So all you need to do is put a negative sign right there. And now that equality is true. All right, below the negative integral of negative sine x dx, you have the integral of secant squared x dx, which is equal to tan x plus c. And then over on the right-hand side, you have 3 other integrals. You have the integral of what, secant x tan x dx. And of course, that's equal to the secant x plus c. And then because I know this one, I naturally know this one, so negative cosecant x cotan x dx. Since that was secant, this must be cosecant x plus c. And again, if they don't have the negative sign there, you just make this negative, just like you did before. And then the final one, I have the integral of minus cosecant squared x dx. And that's just going to be equal to, right here, cotan squared x. Oops, just cotan x. And again, the way I remember this one is I know this one over here, and it should have the same sort of form, just the cotan. So cotan of x plus c. So those are the normal trigonometric functions. So let's just do part A so you can see this one. So you have the integral of sine x plus cosine of x dx. And a lot of times when I do trigonometric functions, it's more of a guess and check. So I say, okay, integral of sine x, let's just guess, maybe that's cosine of x. Plus on the integral of cosine of x is, oh yeah, sine of x. And then all plus c. And then I want to check my work because maybe I made a mistake. Maybe I'm off by a negative sign, sometimes. So to check my work, I say, okay, the derivative of cosine of x is negative sine of x. Oh, and I have positive. So I just need to put a negative sign there, and I'll take care of that. So derivative of negative cosine of x is negative sine x, which is positive sine x, plus derivative of sine x is cosine x plus 0. So this one's good. So that's typically how I do integrals with trigonometric functions that are one of my types now. So now I had 4 types before, and now I have 10 types. Right? So it's just recognizing the types and then using the appropriate rule. Now part B is going to use inverse trigonometric functions. So let's talk about these. So if you look on your sheet, it tells you that if you have the integral of 1 divided by the square root of 1 minus x squared dx, that's equal to sine inverse of x plus c. Whereas if you have the integral of minus 1 over the square root of 1 minus x squared dx, that's equal to cosine of inverse of x plus c. And then finally, you have the integral, probably one of the most important ones here, 1 over 1 plus x squared dx, and that's equal to tan inverse 1 of x plus c. And so let's use these in part B. So in part B, we have the integral of square root of x minus 1 over 1 plus x squared dx. And before I can integrate this, I'm going to write this as a power, because again, I can only integrate now. I can integrate constants, I can integrate powers, I can integrate I can integrate exponentials, e to the x's, okay? I can integrate 1 over x, and I can integrate some trig functions and some inverse trig functions. So I need to write this as a power function. That's one of the things I can integrate. Minus, I'll keep this the same. There's nothing I can do here. And that's good because it's one of my types, right? I no longer have 4 types. I have lots of types now, but it's one of my types. I think I have 13 types really. But here, that 1 over 1 plus x squared is this type. So I apply the rule and get tan inverse of x, of course, plus the c. So now I add 1 for the power rule, and if I add 1 to 1/2, I get 3/2, and then divide by it. Minus the integral of 1 over 1 plus x squared is just tan inverse of x, and that's all plus c. And I want to clean this up a little bit because they gave it to me in radical form. I want to put it back in radical form. So this is equal to 2/3. You divide by a fraction, same as multiplying by its reciprocal. X to 3/2 is simply x root x. And then minus my tan inverse of x plus c. And that's my answer. Again, you can check your work. I'd probably check it from up here. 3/2 comes down, cancels at the bottom. Then take away 1, so it's x to the 1/2. And the derivative of tan inverse of x is 1 over 1 plus x squared. And everything checks out. Right? Check. Okay, so now what we want to do is we want to start using the fundamental theorem of calculus to evaluate some definite integrals. So here's a definite integral right here. And we want to check our work with a calculator. And so I always let's just get the calculator going right now. All right, so let's, for my calculator, the idea is we can graph this thing. All right, because I say integral, you say area. So we can graph x minus 2 over x and make our window go from 2 to 4, because that's where the limits go from, 2 to 4. And then we'll zoom fit it. And you can see here, we get this picture. So if you plug this in, you get this picture here. And we're going from 2 to 4. And we're trying to figure out this area, really. And it is an area because it's above the x-axis, I'm guessing. So we can trace this. You can trace this and see it is above the x-axis. And we hit second trace, and we can hit number 7. And we can do 2 enter, 4 enter, and watch the region get shaded in. And everything looks good. All right, so we should get out approximately 4.61. So this area is approximately 4.61. So let's see if we can do this. This is equal to, and we want to integrate x. All right, so we simply add 1 to it and divide by it. So you get x squared over 2 minus the integral of 2 over x. Well, this is just 2 times ln, absolute value of x, plus c. Oh, and this is a definite integral, so we don't need plus c. Remember, definite integrals, we don't need to write plus c because we'll add c and subtract c, so they always cancel. But we do need to write down the limits of integration, so this is from 2 to 4. Oh, and let me make sure, did I write ln of absolute value? Oh yeah, I did, up there, okay. Sorry. So back down here, if you plug in 4, what do you get? So you get 4 squared over 2 minus 2 ln of absolute value of 4, which is just 4. So you don't need to write the absolute values on it because 4 is already positive. Minus, and then you have 2 squared over 2 minus 2 ln of 2. You don't need to write the absolute values because 2, again, is already positive. And so this is going to equal to, you have 16 over 2, which is an 8, minus 2 ln of 4. And then minus, you have 2 squared, which is 4 over 2, so minus a 2. And then minus a minus is a plus 2 ln of 2. And this is equal to then 6. And then you have, because 8 minus 2 is 6. And then you have minus 2 ln of 4 plus 2 ln of 2. And let me tell you, this is a fine answer. You could, I'd take this answer, no big deal. You know, you just write it down, it's fine. But if this is a multiple choice question, you might see the answer, instead of written like this, you might see it written as, let's say, 6 minus ln of 4. And then you might see it written like that. Right. And why is this equal to 6 minus ln of 4? Well, the idea is this. Remember, these exponents can go up in the power, so I can write 2 up here. So this is really equal to 6 minus 2 ln of 4 plus ln of 2 squared, which is ln of 4. If you have 1 ln of 4 and you take away 2 ln of 4, so you're left with a loss of ln of 4. So it's 6 minus ln of 4. Let's check it, see if it's right. See if we made any mistakes here. So I have 6 minus ln of 4. In parentheses, hit enter. And we get out the same answer, so it checks. It's good. All right, the second thing we want to do on using the fundamental theorem of calculus is we want to try to find the area between two curves. And so we're going to do 2 problems. And we want to find the exact area, which means you need to do this by hand. And so the first problem is going to be relatively simple. We want to find the area between these 2 curves. And sometimes it's always useful to get this going on your calculator. And so let me just show you real fast. The idea is this. Here's my x and y axis. Here's one curve. So here's my f of x. And here's another curve. Let's call this g of x. So here's my g of x. And of course, when you look at this, you see that there is some area between the 2 curves. So here it is right here. And I want to try to find that area in blue. And the way you do this is you take the integral you always take the upper curve minus the lower curve. So I take f of x, integral of f of x minus g of x dx. And understand what you're doing here. And, you got to find these limits. So you need to find where they intersect. And I don't know where that is, so let's just put question marks. So for your limits of integration, you have these question marks. And it's a real simple idea if you think about it. And I can color code this, and you can tell me exactly what's going on. So if you do the integral of f of x, you get this area between the 2 question marks. And of course, if you do the integral of g of x between the 2 question marks, you get the green. And suddenly you realize the blue area, the area in blue, is equal to, and you say, oh yeah, the area in black, take away the area in green. And that's all you're doing here. So you always take the upper minus the lower. So when you take off the area above, which is the integral of f of x dx, from the area below, which is g of x, so g of x, integral of g of x dx, you get the area of the blue, the area in between. And so on my calculator, what you can do is you can plug this in. So I have x raised to the 3, and I have 1 minus x in parentheses, and there's too many 1's there. So let's get rid of those 1's. Should be just 1, 1. And then the x-axis, well, that's just y equals 0, so you don't need to put anything for that. And then, you don't know what to make your window, so I just do a standard window, which is minus 10 to 10. And the problem we're going to have here is you're not going to be able to see really the area enclosed by this curve here and the x-axis. So what you need to do, so x-axis is y equals 0, is to actually do this problem. You need to figure out where the heights are the same. So if y is equal to 0, you just set y equal to 0 and solve for x. So down here, let's do part A. So if I was going to do part A, I'd take 0 and set it equal to x cubed 1 minus x. And the reason it's 0 is because when y is equal to 0 is the x-axis, and I want to figure out when this curve here meets that curve there, so I just set them equal to each other. And so 0 is equal to that. And so I have x equal to 0 or 1. This tells me where to look, so on my graph, instead of looking between minus 10 and 10, I'll look between 0 and 1 and zoom fit it, and you should see that the curve meets the x-axis between here. And there it is. All right, so we're trying to find this area in between right here. So let's draw a picture of what I'm trying to do. So I have right here, I'm going between 0 and 1. And it looks like this. And I'm trying to find this area. And so A is equal to, and I always like to draw a little rectangle inside here to help me out. So I'm just trying to find the area of that one little rectangle, and then the integral will add it all up. And so this is equal to the integral between 0 and 1. So between 0 and 1 of my function, so this turns out to be x cubed 1 minus x. Right, this height, which is given by my function right here. And then I have a dx there. And so now I just need to figure out what this integral is. So this is integral from 0 to 1 of x cubed minus x to the 4th dx. I'll multiply through by the x cubed, and I get to get power functions. And so I add 1, so I get x to the 4 divided by 4 minus x to the 5th divided by 5 from 0 to 1. I plug in the upper limit, which is a 1, so I have 1/4 minus 1/5. Minus, now when you plug in 0, you're just going to get 0 out. And so this is equal to, I have to find a common denominator. So I multiply top and bottom by 5 for the first one, and then top and bottom by 4 for the second one. And I'm going to get 1 over 20 units squared. Because it's an area, I'll put units squared on it. And I can check my answer with my calculator. So second trace, go down to number 7, and lower bound was 0, upper bound was 1. And I should get 0.05 out, and I do. So it checks, it's good. My arithmetic and algebra are sound on that problem. Now part B is a little bit more complicated. Right, so part B, what I have is y equals x cubed and y equal to x. Again, I can try to graph this. So y equals, I have x raised to the 3. I have an x. I don't know what to make the window because I haven't done anything, so I'll just do a standard window. And when you do this, it's hard to see how these things actually cross. Right, you see that they probably cross somewhere around here, but it's hard to see. Now you can zoom in and figure that out, but better yet, what you should be able to do is you should be able to realize when they cross, like up here on this picture, when the curves cross, their heights are the same. Right? Their outputs are the same. Their y values are the same. So just set them equal to each other. X cubed is equal to x. And then try to solve for x. And again, I don't divide by x because I lose solutions. I lose a solution x equals 0. So I just set them equal. And I subtract 1 from the other side. I factor out. So I get x times x squared minus 1 equals 0. Of course, I can factor this. That's x minus 1 times x plus 1. Equals 0, and this gives me all the answers I need. So x equals 0, 1, and -1. So on my calculator, what I'm going to do is I'm going to take my window and I'm going to set -1 to 1 and zoom fit it, and you're going to get a beautiful picture. All right, so here's my beautiful picture. And so I see exactly where they intersect, and so I'm looking for all this area here and this area here. So let's draw a picture right here of what I just did. And so it looks like something like this. So it comes up and goes up like this, and then there's a line right here going through here like that, and I went from -1 to 1, and I'm looking for this shaded area, and that's 0 right here. Alright, so to find this, there's actually two ways to do this. You can break it up into two different problems, because I want to find this area here and this area down here. So I like to draw little rectangles in there to remind me. I'm just trying to find those areas, those little rectangles, and the integral will find the rest. This is y equals x, and then this one up here is y equals x cubed. And you can do this again two ways. I can call this area 1, and I can call this area 2. And so I know the area is equal to area 1 plus area 2. And so that's equal to area 1 is the integral from -1 to 0. And on top is x cubed, so I'll have x cubed minus x dx, plus area 2, I'll do the integral from 0 to 1. And now on top is x now, so this is x minus x cubed dx. And I can evaluate each of these integrals separately and get the right answer. But I could also, another way to do this is to realize that this area, area 1 and area 2, are exactly the same. So if I want to find the area in black, I could simply just do 2 times A2, because they are, in this case, they are the same. Now you have to be careful, right? They're not always going to be the same. It's the same because this function x cubed is odd, right? And so is y equals x. Right? So these are going to be exactly the same areas. So I could also do this one, the integral from 0 to 1, and multiply it by 2 of x minus x cubed dx. And so if you did it that, it'd be 2 times, and then 2 times all of this to the integral of x, so that's x squared over 2, minus x to the 4th over 4 from 0 to 1. And then I can plug in 1. So I have 2 times, I have 1/2 minus 1/4. Then minus 2 times, and when you plug in 0, you just get 0 out there. And so this is equal to 2 times. And then 1/2 minus 1/4, well, this is going to be 2 over 4, then minus 1 over 4. And so that's equal to 2 times 1/4, which is equal to 1/2 units squared. Now you do need to be careful here. If they're not symmetric, if these areas are not the same, the functions aren't symmetric here, the areas won't be the same. So you might be safer just by doing 2 definite integrals so you don't make this mistake. Now you can check your work. Sometimes it's a little hard to check your work with this, but you certainly can calculate the area. So on 7, you could calculate the area to the right under y1 equals x cubed, so I can do from 0 enter to 1 enter, and it's going to shade in this little region here. So you know that's 0.25, so I could write down that number, and then I can figure out the integral under y equals x. So hit second trace again, go down to the integral, and now just make sure you use your up or down arrow so you wind up on x. So now I'm on x, use 0 enter 1 enter, and it says it's 0.5. Okay, so 0.5 minus 0.25 is, again, 0.25. So I know the area right here is 0.25. And again, you can multiply by 2 and you get 1/2. So you can check your work. So this does check. And so let's zoom out just a little bit so you can kind of see what we did here. So how the problems are basically the same. So here, first step is really to find out where these functions meet. All right, so I found out where the functions meet here. Right, so you can kind of see I did that there, and I did it here. Once you find where they meet, you can make your window on your calculator, and you can get your graph. So here's my graph. Here's my graph. And then I have to write the formula basically, or the equation for the area. So A is equal to what in this case? A is equal to, what in that case? And then actually integrate it out to get my answer.